Guys, and welcome back to our channel. In this particular lesson on math mechanics, we are presenting the lesson inclined planes. Inclined planes. In a previous lesson, we discussed about strings, tension, and so on. So please don't forget to subscribe and to watch this video to the end. We are going to be unfolding a lot of beautiful packages inside this lesson just for you. So first of all, what is an inclined plane? What is actually an inclined plane? An inclined plane is a flat supporting surface tilted at an angle. A flat supporting surface tilted at an angle with one end higher than the other, just like you can see. And it is used for raising or lowering loads. An inclined plane is also known as the ramp, and is one of the 6 classical simple machines defined by Renaissance scientists. Let us consider an inclined plane which is horizontal, or a plane which is inclined horizontally as shown at an angle theta to the horizontal. So this is a plane which is inclined at an angle theta to the horizontal, that is the angle, and with a mass m on it. A mass m on this plane. The body is subjected to move only along the plane, even though gravity acts downwards. So this particle, normally since gravity acts downwards, but this particle cannot move downwards, it can only move along this plane. So the weight W acts downwards for this inclined plane, the weight W acts downwards, and this weight is equal to the mass times gravity. So the mass is m and gravity is g. This weight can be resolved into its components parallel as follows. So the component of this weight parallel to the plane is mg sine theta, that is the weight sine theta. Then perpendicular to the plane, it is given by mg cos theta. That is when the angle is at this position. So if the angle is at this position, this component parallel to the plane is mg cos theta. The normal reaction, according to Newton's third law of motion, action and reaction on the plane, the normal reaction on this plane is given by R. Equally, if the plane is smooth, then the coefficient of friction is negligible, or we say it is equal to 0. That is if the plane is smooth, like you saw in the previous video. If the plane is smooth, then we have friction to be equal to 0. However, if the plane is not smooth, if the plane is rough, then we will have friction given by F equals mu R. Because the tendency of this object is to slide down this plane. So friction will normally act in the opposite direction. So since the tendency for this particle to slide down the plane, the friction should act upwards. With this, we have mu. This mu here is the coefficient of friction between this object and the plane. Mu is the coefficient of friction between the object and the plane. From this point, other additional external forces can be added to the system, which we are going to discuss in the course of this tutorial. Please, if you have not subscribed, subscribe and click on the notifications so that whenever we release a new video, you're automatically updated and notified. So for this case, if the particle is static, in this particular case, if this particle is static, then we'll have the following equations. We'll have this mg sine theta to be equal to mu r, that's equation 1. That's along the plane or parallel to the plane. Then perpendicular to the plane, we will have mg cos theta is equal to r, equation 2. That's if this particle is static. And if we divide equation 1 by equation 2, then we will have mu to be equal to tan theta. So a tan theta will be equal to mu, and you can do this by dividing equation 1 by equation 2. So these are the 3 main basic equations for inclined planes. But there is one other thing that you have to be aware of. This is a very powerful remark. So this very important remark is when the angle is no more at this down position. Okay, so let's see something. So if the particle is no more at this position down here, let us see what happens. So if the angle is moved upwards, as you can see, then there will be a swap of this cos and sine. See what happens? These components perpendicular to the plane of this weight will now be the cos theta, the sine theta, while these components parallel to the plane will be cos theta. So if the angle is at this position, then this is how the forces will be resolved. Take this very important remark, which is very, very important when you have constraints in an examination hall. So note this. And our equations, if the system is in equilibrium now, the equations now become mg cos theta equals mu r, equation 1, and mg sin theta equals r, equation 2, and our mu will be given by, mu will be equal to 1 on tan theta, and tan theta will be equal to 1 on mu. Let's take the first example. The first example reads, a particle P of mass 2.5 kg rests in equilibrium on a rough plane under the action of a force of magnitude x newtons acting on a plane of greatest slope, as shown. So this is the x acting on this particle P. The plane is inclined at 20 degrees to the horizontal, as you can see. The coefficient of friction between P and the plane is 0.4. The particle is in limiting equilibrium. Limiting equilibrium means the frictional force is equal to mu r, and is at the point of moving up the plane. So this particle is at the point of moving up the plane. Calculate A, the normal reaction of the plane on P, B, the value of x, C, the force x newtons is now removed. Show that the particle remains at rest. So let us look at this question. So we have resolving P, or starting with the weight, since P is 2.5 kg, so times G, that will give us 2.5 G. That's the weight, 2.5 G. Then starting by resolving the forces on P normal to the plane, since R is unknown. So start with the normal to this plane, since R is unknown. So this will give us 2.5 cos theta, G cos theta, and normal to this plane, this other force in this direction should be equal to R, as we saw before, okay? And then, since this force is pushing this thing upwards, friction should normally act in the opposite direction. The particle is about moving up the plane, so friction should act in the opposite direction, and that will give us F, which is our mu R. Then, equally, if you resolve this weight parallel to the plane, the components down in this direction will be 2.5 G sine 20. So we have resolved for all the forces acting on this plane. Now, so the first one, perpendicular to the plane, we will have R minus 2.5 G cos 20 to be equal to 0, since this particle is stationary or static. So this will give us R to be equal to 2.5 G cos 20, which is equal to 23 newtons to two significant figures, 23 newtons to two significant figures. Now, equally, we have x minus f, because x is acting upwards, while 2.5 G sine 20 and f are acting downwards. So x minus f minus 2.5 G sine 20 is equal to 0, since the particle is stationary. And this will give us x to be equal to f plus 2.5 G sine 20. And how do we get f? F will be equal to mu r, okay? We already have the value of r, right? So this will give us mu r plus 2.5 G sine 20. And our mu from the equation is 0.4. So we have 0.4 times 23 plus 2.5 G sine 20. And if we simplify all of this, we'll have 17.6 newtons as the force x. The force x is 17.6 newtons. Okay. Now for the C part of the equation, so when the force x is now removed, so if this force x that is about pushing this particle of the plane is removed, what will happen? this particle will now normally slide down the plane, provided the limiting friction is not exceeded. Okay, it should normally slide down the plane. So when it's now removed, what becomes of this diagram? So we have to draw a new diagram. This will now be what we will have, because the force X is no more there. Now, the only change that we have here is along or perpendicular to the plane. None of the forces has changed. Everything has remained the same. But parallel to the plane, one of the forces has altered. So here we will still have F minus 2.5 G sine 20 to be equal to 0. That is normal to the plane. And that is a parallel to the plane. This is what we have, F minus 2.5 G sine 20 equal to 0. And our F will equal to 8.38 newtons to 3 significant figures. Now, equally, normal to the plane, we have R minus 2.5 G cos 20 equals 0. And our R will still remain the same, 23 newtons, like we said before. So R has not changed because none of the forces that are normal to the plane has been altered. Now, the next thing is to find mu R. And mu R is equals 0.4 times 23, which is 9.21 newtons. Why are we doing all of this? We are doing all of this because we want to show that friction is not limiting and equilibrium is maintained. When we have F is equal to 8.38, that is a frictional force. And what is the normal reaction? Friction here is also giving us 9.21. So this shows that friction is not limiting. And what is this condition? So here we find F that will maintain equilibrium and check if F is less than mu R. So our F here is 8.38, where our mu R is 9.21. If F is less than mu R, then we conclude that the particle will not move, that equilibrium will be maintained. But if F is greater than mu R, then the particle will slide down the plane. Okay. So here we find F that will maintain equilibrium, then check if F is less than mu R. And mu R is 9.21, F is equal to 8.38. And we have seen that F is less than mu R, so the particle will not slide down the plane. Let's take another example. Example 2, a parcel of weight 10 newtons lies on a rough plane inclined at an angle of 30 degrees to the horizontal. A horizontal force of magnitude P acts on the parcel as shown. The parcel is in equilibrium and on the point of slipping up the plane. So the particle is at the point of almost slipping up the plane. The normal reaction of the plane on the parcel is 18 newtons. The coefficient of friction between the parcel and the plane is mu. Find A, the value of P, and B, the value of mu. The horizontal force is then removed. Determine whether or not the parcel moves. So as usual, we start by resolving the forces. So we have the weight. The weight is given by 10 from the equation. Then its components, we have normal to the plane, we have 10 cos 30. Okay. Then parallel to the plane, we have a 10 sine 30. Then the normal reaction is given by R. The normal reaction in the equation has been given as 18. So this is the 18. Now F acts downwards because this force is about pushing this, this P is about pushing this particle up the plane. So normally F should act in the opposite direction, downwards. So that's our F. F acts in the opposite direction of P. Now the next thing to do is we resolve this force P into its components. When we resolve this force P into its components, the volume down the plane, we will have a P cos 30 that will be acting in this direction. In fact, in the direction up the plane. So now, normal to the plane, we'll have 18 minus 10 cos 30 minus p sine 30 to be equal to 0. And from here, our p will be 18 minus 10 cos 30 on sine 30. That will be the value of the force P. So our P will be 18.68 newtons to four significant figures. Then along the plane, we have P cos 30. Along the plane, so we have P cos 30 minus F, that's acting in the opposite direction, minus 10 sine 30 to be equal to 0. And from here, we'll find our F to be equal to this 11.2 newtons. So F will be equal to 11.2 newtons. Now, at limiting friction, we have F to be equal to mu r. At limiting friction, this is what occurs. F is equal to mu r. The particle does not move. So from here, mu will be equal to F on r. F that we have solved for is 11.2 divided by 18, which is r. And this gives us 0.62 to two significant figures. When P is now removed, so when P is now removed, what will happen? When P is now removed, F will now act upwards. So if you remove this force P, this F that was acting downwards because it was about moving up, so friction is acting opposite direction. When you remove the force, the particle will now want to move downwards and friction will be acting upwards. And this is the diagram that you have. So F has the reverse direction when P is removed, right? So this one you must take note of. So at this point now, if equilibrium is maintained, then you will have F minus 10 sine 30 to be equal to 0. F will be equal to 10 sine 30. Thus, F is 5 newtons. And normal to the plane, we'll have R to be equal to 10 cos 30. In this particular example now, R has altered because this force P affects the forces on both planes, that is parallel and perpendicular to the plane. So our R now will be equal to 10 cos 30. Our R will change in this case. The forces have been altered in both parallel and perpendicular to the plane. So this gives us R, please, not that. So this gives us an R to be 8.66 newtons, okay? 8.66 newtons. However, the coefficient of friction on the plane does not change. And we know that mu r should be equal to 0.599 times 8.66. Okay? Because mu that we calculated was that, and then you have 0.86, which is r. So since our mu does not change, we have, so since our mu still remains the same 0.62, when we multiply by r, we are going to have 5.373 significant figures. And here we obtain, you see that F, which is 5 newtons, is less than mu r. So this means that equilibrium is maintained. And the equilibrium is not limiting. If F was equal to mu r, then we say it's a limiting equilibrium. But if it is less than, we say equilibrium is not limiting. However, note that if F is greater than mu r, then the particle will move. So in this case, the particle the parcel does not move. Example 3, a particle of mass 0.5 kg rests on a rough plane rather. This example is a rough plane, inclined at alpha to the horizontal, where tan alpha is 3 on 4. The particle is held at rest on the plane by the action of a force of magnitude 4 newtons, acting up the plane in the direction parallel to the line of glacial slope of the plane, as shown. The particle is on the point of slipping up the plane. A, find the coefficient of friction between P and the plane. Let's find this coefficient of friction. So we start by resolving, by looking for the weight of P. That is going to give us 0.5 g because the mass is 0.5. Then we resolve its components into parallel and perpendicular to the plane. So we have 0.5 g cos alpha, and down the plane we have 0.5 g sine alpha. The normal reaction is given by R, and friction acts in the opposite direction of this force that is pushing about pushing this particle up the plane. So now normal to the plane, we will have R minus 0.5 g cos alpha to be equal to 0, since the particle does not move. R will be equal to 0.5 g times, so they'll give us tan alpha to be 3/4. So from trigonometry, if tan alpha is 3/4, then cos alpha will be 4/5. So you can draw the triangle and then you see. So this will give us 3.92 to 3 significant figures. That's the value of R. Now along the plane, we have 4 minus F. So along the plane now we have 4. Let's see, we have these 4 newtons minus F minus, so this is the 4 newtons that's pushing it upwards, and minus F is acting downwards, minus 0.5 g sine alpha is acting downwards. That should be equal to 0. So from there, F will be 4 minus 0.5 g times sine alpha. So sine alpha will be 3/5. So from here, we have F to be equal to 1.06 newtons to 3 significant figures. Now, since the question talked about limiting friction, because the particle is on the point of slipping up the plane. The point of slipping up the plane means the particle is at limiting friction. And what happens at limiting friction is that F is equal to mu R. F will be equal to mu R. So you put in these values that we have, 1.06 divided by 3.92, that will give us 0.270 significant figures. Now the B part of the question says that find the acceleration of P down the plane. The question begins by saying that force of magnitude 4 newtons is now removed. So we have removed this 4 newtons force. Let us draw the new diagram. So this is what we are going to have. When this force is now removed, this particle will now slide down this plane, and they want us to find the acceleration. So the acceleration is downwards, as you can see. So just before, F is equal to mu R, and our F is equal to 1.06. And since the forces perpendicular to the plane are unaltered, since this force of 4 newtons was parallel to the plane, so it does not affect the forces perpendicular to this plane, which therefore means that our F still remains 1.06, and mu remains the same too. So parallel to the plane, we will have 0.5 g sine alpha minus F as the frictional force. So the frictional force remains the same, is equal to 0.5 times the acceleration of this particle. So our acceleration will be equal to 0.5 times 3/5 minus 1.06 divided by 0.5. So the acceleration down the plane is given by 3.76 meters per squared second. So 3 significant figures. That's the acceleration of this particle down the plane. Guys, please don't forget to subscribe to this channel and to leave your notifications. You can give us ideas on the type of videos you would like us to do, and equally on the quality of our videos, and give other proposals. Please subscribe, click on the notifications, and to support our work, please share our videos to all your social media platforms that others may benefit from this work. Thank you so much, and stay tuned. That brings us to question 4. The diagram shows a boat B of mass 400 kg held at rest on a slipway by a rope. So it's held at rest by this rope on a slipway. The boat is modeled as a particle. So they consider this boat to be a particle, and the slipway is rough, inclined at 15 degrees to the horizontal. So this plane is rough. The coefficient of friction between B, that's the particle, and the slipway is 0.2. The rope is modeled as a light inextensible string parallel to a line of greatest slope of the plane. The boat is in equilibrium. and on the point of slipping down the slipway, so it's at the limiting equilibrium or limiting friction. Calculate the tension in the rope, that's the A part. So we first of all start by, this is the diagram. We have the weight is 400 times G, so we have 400 G. Tension in the string is pulling the object upwards, okay? And then, so we equally have F, which is acting, okay? So they say that the object is on the point of sliding, right? Sliding down. So this is about sliding down the plane. And since about sliding down the plane, then friction should act upwards. Okay. Normally tension is pulling the object upwards and friction is also acting upwards because it's about sliding down the plane. So at this point now, resolving these forces for the components that are normal to the plane, we'll have R minus 400G cos 15 to be equal to 0. And R will give us 3,786 newtons. Then, as limiting friction is involved, it means that F is equal to mu R. So you can find F, the force F. Okay, so the force F will be equal to 0.2 times R, because F is equal to mu R. And mu has been given as 0.2. So F is equal to mu R. Okay. Now, still parallel to the plane, therefore, when we resolve, we can now find T. So the parallel to the plane, you have T plus F because they're acting in the same direction. Now, minus 400G sine 15 degrees is acting down the plane, should be equal to 0. And you have a T to be equal to 400G sine 15 minus F, giving us G to be equal to 257.3 newtons. All right, so 3 significant figures, and so 2 significant figures, we have it as 260. Okay. Now that's A. Now for the B part of the equation, we are told that the boat is 50 meters from the bottom of the slipway. So it's 50 meters away, as you can see on the diagram. And the rope is detached from the boat and the boat slides down the slipway. Calculate the time taken for the boat to slide to the bottom of the slipway. So now when this rope has been removed, the resultant force is 257 newtons that acts down the plane. Why are we saying the resultant force is 257 newtons? So because when this tension has been removed, we know that T was equal to 257.3. So this will be the exact force that we now use to move down the plane. We know that acceleration is constant. So from Newton's second law, we have force is equal to mass times acceleration. So this 257 should be equal to the mass of the object times its acceleration. And that gives us 0.643 as acceleration of the particle down the plane. Now we can consider the motion down the plane as we have U. Initially it was at rest, so U is 0. And then alpha, the acceleration is 0.643. The distance is 50. So we can use the equations of motion. S equals ut plus half at squared. We substitute our values and our t will be 12.5 seconds. At t will be 12.5 seconds. Okay. Now the next question reads as question 5. A heavy package is held in equilibrium, as you can see, on a slope by a rope. The package is attached to one end of the rope and the other end being held by a man standing at the top of the slope. The package is modeled as a particle of mass 20 kg. The slope is modeled as a rough plane inclined at 60 degrees to the horizontal, and the rope as a light, inextensible string. The string is assumed to be parallel to the line of graded slope of the plane as shown in the diagram. At the contact between the package and the slope, the coefficient of friction is 0.4. A, find the minimum tension in the rope for the package to stay in equilibrium on the slope. So in this particular one, we come in contact with the terms finding the minimum tension. So we are going to solve inequalities. Whenever you have about minimum or maximum of anything, it means that inequalities are being involved in the solving. So either use greater than and less than in our solutions. Okay. So this is a diagram showing all the forces acting, and the friction is directed up the plane to prevent slipping down the plane, because this object is about slipping down. It's about slipping up rather. So friction should act downwards. This one is holding it and pulling it upwards. That's why the tension is towards him. So the particle is about moving up. The friction should therefore be acting in the opposite direction. So let T be the minimum tension. Okay. So let T be the minimum tension. F, the force of friction, and R, the normal reaction. So this is what we'll have. Then at this point, perpendicular to this plane, you have R minus this component. So R minus 20 cos 60 as perpendicular to the plane should be equal to 0. Those are the little forces, right? So R is 98. Then as the friction is limiting, we'll have F to be equal to mu R. Okay, and that will give us 0.4 times 98, which is 39.2. That is the friction. Now we have finished with normal to the plane. Now let's move parallel to the plane. So parallel to the plane, we'll have T plus F to be equal to T plus F minus 20G sin 60 to be equal to 0. And therefore, T will be 130.5 newtons. That will be the value of T. Now, the man pulls the package up the slope. Given that the package moves at a constant speed, find the tension in the rope. So now there is motion. And since there is motion, this is what we have. The man pulls it up the slope. So R is as before. He's pulling up the slope now. So there is nothing has changed to the components perpendicular to the plane. So R will remain the same. Okay. So R is the same as before. And as the particle is moving, friction is limiting. Okay. So friction is limiting. F is 39.2 as before because friction is constant. So F equals mu R is the same as in part A as we have just explained. So with this particle, we have T minus F minus 20G sin 60 should be equal to 0, and T will give us a value of 209 newtons. So that will be the value of our T, 209 newtons. Why is this like this? Because since the man is pulling the package at the constant speed, we're supposed to say it's equal to mass times acceleration here. But if the particle is moving at constant speed, what happens to the acceleration of the particle? Normally, you are considering the speed here as the velocity. So if you do a constant velocity of the plane, because there is a direction, it means that the acceleration is 0. So mass times acceleration here will give us 0. That's why you have equal to 0 on the right-hand side. Now, C states how you have used in your answer in part B, the fact that the package moves 1 up the slope and 2 at constant speed. So friction acts down the slope and has a magnitude of 0.4 R. So friction opposes motion. This is the idea I've used. And for moving at constant speed, there is no acceleration as I've just explained. So the net force on the package is 0. And that's why we use this equation like this. This is according to Newton's first and second laws of motion. Don't forget to subscribe and to click on the notifications bell and to leave your comments. We have other videos on math mechanics. You can visit our channel, GCE Math Panel, on YouTube, or www.gcemathpanel.blogspot.com, where you have more materials on this. Now, let us look at this other question here. What's the minimum force to keep this block from sliding downward from rest? So if you look at this block, this angle theta is 35 degrees. The weight of the block is 500 newtons. And frictional force is equal to normal reaction times mu s. So we have mg cos theta to be equal to our frictional force, this is FFR of the plane. So what is the minimum force to keep the block from sliding downwards? So we want to calculate the minimum force F that will prevent these particles from sliding downwards. So here we have to solve the equation F, since F is acting upwards and mu s also acting upwards, mg sin theta is acting downwards. So you have F to be greater than mg sin theta minus mu mg cos theta. Okay, so when you solve this equation, you start the minimum force with 164 newtons. 164 newtons. So solve this equation, and this is what you'll find. All right, now number 7, a box of mass 25 kg is placed on an inclined plane that is at 40 degrees angle with the horizontal as shown. Determine the normal force Fn and the force parallel Fp. So F perpendicular and Fp, this one is just a child's play, right? So cos 40 will be equal to the force that is perpendicular, because this is 40, right? So this will also be 40 at this point. So cos 40 will be equal to opposite of a hypotenuse. And this opposite is the force that is parallel to the plane, the same force that is parallel to the plane, all over the hypotenuse, which is the weight, on 245. So this force that is perpendicular will give us a value of 188 newtons. Now for the force that is parallel to the plane, we will have sine 40, still with this triangle, sine 40 should be equal to opposite, that is the force that is parallel, over hypotenuse. So from here, the force that is parallel because 245 sine 40, which is 157 newtons. So that is what we have for this. And as a summary, what is the coefficient of friction? The coefficient of friction is the magnitude of the frictional force that satisfies the inequality. In one of our previous lessons, we are discussing about friction. So but we are just revising it here. So F is the friction, and R is the normal reaction force between the object and the surface. Mu is the coefficient of friction between the object and the surface. If there is no friction, then mu is 0. As friction is negligible, and you see the surface is smooth. Otherwise, if the surface is rough, then mu should be greater than 0. The maximum possible frictional force is given by the equation F max equals mu R, and this is what we call limiting friction, the maximum possible frictional force. So F max is the maximum possible frictional force, also called limiting friction. So F max serves as limiting value for problems in mechanics involving friction, okay? So now the first thing is, if the object is stationary and the resultant of the other parallel forces is less than or equal to F max, then the object remains stationary like we saw in the examples. The frictional force is always equal and opposite to the resultant of the other horizontal forces. If the resultant of other horizontal forces is equal to F max, then the object is said to be in limiting equilibrium. Now the second case, if the object is stationary and the resultant of the other horizontal forces become greater than F max, the object begins to accelerate. So if X is greater than F max, the object begins to accelerate in the direction of the resultant force, and the frictional force is equal to F max with the direction always opposite to that of the object's motion. Friction always acts in the opposite direction to the object's motion. If the object is in motion parallel to the surface, then regardless of the other forces, the frictional force will always be equal to X max with a direction opposite to that of the object's motion. And lastly, this diagram, so when you have forces on an inclined plane like this, and this angle here is theta, then the weights can resolve into its components. Perpendicular to the plane, you have mg cos theta, and parallel to the plane, you have mg sin theta. Friction acts in the opposite direction like this, and that's a normal reaction. Next, and we have these three equations. If the angle of angle theta is now up here, the equations will also reverse. At this position, we will have, so if the angle is reversed, this cos theta and sin theta also reverse their positions like this. Okay, so that's what we have. And the system is, if the system is in equilibrium, we have these equations now in this form. So take note of this. Thank you so much for watching this video. And in our next videos, please do not forget to subscribe and click on the notifications. Subscribe and click on notifications so that when you upload any new video, you're notified at once. Thank you so much for sharing our videos because we know you are going to do that. Also watch inclined planes, projectiles, momentum, work energy, and power. And our next video is on projectiles. Please subscribe, share our videos, leave your comments, and stay tuned. Bye-bye.